Good morning everyone, and welcome to today's worked exam answer video. Today I am exploring an A-level question which could also come up on the AS papers from the AQA specification, looking at oxidation, reduction, redox, and then there's a lovely application question at the end where we're going to have to use the reactions that we've written already in the question, albeit for a different halide ion, to have a think about what would happen with a second halide ion in a very similar reaction. So, as always, I'm going to do some annotating and highlighting, but one of the things that I'd really like to do here is show you live how I would go about writing the half equations, because sometimes students can try and do too much of this in their head and want to write the whole thing out in one go in a specific order. I would not suggest that's the most effective way of doing things, and I would like to show you therefore how I would approach writing a half equation. Not saying that my method is the only way that you can do things, but I do think that some of you may find it helpful. Hopefully you will. So as I said, a couple of annotations, bit of highlighting, and then I'll come back and I'll be writing the half equations live. Okay, here we go. So the question starts by telling us that a student oxidized a solution of hydrochloric acid with a few drops of sodium chlorate, brackets 1, Roman numeral 1, close bracket, solution. Now that 1 in the brackets is the oxidation state of the chlorine, and when we have something that ends with 8, be it sulfate, carbonate, chlorate, nitrate, that means that there is oxygen present. So if we know it's sodium chlorate, we know sodium has an oxidation state of +1. We're told the chlorine has an oxidation state in this compound of +1. There must therefore only be one oxygen to give us the overall oxidation state of 0, which is true for our compounds. So the formula of sodium chlorate is NaClO. We're then told that the reaction mixture effervesced, so a gas has been made and it turned pale green. The gas formed bleached universal indicator paper, so that is suggesting that we are producing chlorine gas. Now that's going to be helpful in part A, where we're asked to write a half equation for the oxidation of chloride ions. We need to, I guess, make the connection that when those chloride ions are oxidized, we would be making chlorine atoms, which, because chlorine is a diatomic element, would go around as Cl2 molecules. But it's also really helpful for part D, where we're going to be thinking about what would happen when we added sodium chlorate to a colourless solution of potassium iodide, so something that contains the iodide ions instead. Knowing that the chloride ions are oxidized to chlorine, that's going to suggest that the iodide ions are probably going to be oxidized to iodine. But of course, we'll come back to that a little bit later. So the first thing I did when I highlighted half equation, oxidation, chloride ions, I then just wrote a little note underneath to say that oxidation represents loss of electrons. And if the chloride ions are losing electrons, then the electrons should appear on the right-hand side. Now for me, and I do this for any half equation, even though I know lots of the half equations off by heart at this point, I would still, and forgive me because like I say, I'm going to do this whilst videoing, which is probably not going to end well. I would start with my chloride ion, and then I'm going to give myself some room in case I need to add anything extra onto the left hand side of this equation. And then on the right hand side, I'm going to put what we're trying to turn those chloride ions into, which is our chlorine atoms, which, because chlorine is diatomic, would need to be Cl2. First step, whenever you're writing a half equation, is to balance the atoms that are not oxygen or hydrogen. So because we've got two chlorine atoms that come together to make our molecules, we're going to need to start with 2 Cl- ions. We don't have any oxygen to balance, which would be step 2. We don't have any hydrogens to balance, which would be step 3. Step 4 is to balance the charges. So the charge on the left-hand side from the 2 Cl- ions is -2. Currently the charge on the right, chlorine as a diatomic element, is neutral. So we're going to need to have our electrons on the right-hand side, which makes sense because for chloride ions to go back to being atoms, they need to lose the electron that they initially gained to go from atoms to ions. And because we've got 2 of those ions, 2 electrons will be lost in total. Doesn't matter that we've got this gap here, just like it wouldn't matter if we ended up with a gap on this side, although you wouldn't tend to on the right hand side because you can write the Cl2 just after the arrow and kind of add along. Alternatively, if we put the 2Cl minus closer to the arrow and then we wanted to add something on the left, we could add it in front of. We don't need to write anything in a specific order on the left hand side or anything in a specific order on the right. So long as everything that's on the left should be on the left and everything that's on the right should be on the right, you'll be absolutely fine. But I think it's helpful to have that as your starting point rather than trying to do all of that in my head and then go, right, okay, the overall equation is 2Cl minus arrow Cl2 plus 2E minus. And you might be thinking for that example, okay, that's a bit straightforward. When we have to balance all the other components, it becomes a little bit trickier, as we're going to have to do in part B. So for part B, we're asked to write a half equation for the reduction, gain of electrons therefore on the left hand side, of chlorate ions to chlorine. Now if we know the formula for sodium chlorate is NaClO, that means that the chlorate ion will be ClO minus because sodium as an ion is Na plus. So we're reducing the chlorate ions, so we're going to start here with ClO minus, and then again I'm going to leave a gap, and then we are reducing that to chlorine, so Cl2. So step one again, we've got to balance the chlorine, so I'm going to need 2 lots of ClO minus. This time we do have oxygens, we've now got 2 of them on the left hand side. To balance oxygens we add water. So because I've got 2 oxygens on the left hand side, I'm going to need to add 2 waters. Now from a practical point of view, we can do this reaction in an aqueous solution. So there will be water present to get this reaction to occur in this way. So it's not random that we've chosen to use water to balance out the oxygen atoms. Step 3 is then to balance the hydrogen, which when we add water brings in hydrogen as well, and there was originally no hydrogen within the reactant or the product. So we've now got 4 H's on the right. We've got to balance that by adding something on the left hand side. Now we can't be adding more water because then the oxygens are going to get imbalanced, so we're going to add H plus ions, and that's what it's getting at here when it says in acidic conditions. So yes, we can do it in water, but we can do it in an aqueous solution by adding an acid, which is depending on what acid, if it's hydrochloric for example, hydrogen chloride dissolved into water, so that would also give us a source of H plus ions, which is what we use to balance out hydrogens. So I'm going to need to add 4 H plus there, and then we balance out the charges. So the right hand side, Cl2 no charge, water no charge. On the left we've got 2 minus charges from the chlorate ions, we've got 4 pluses from the H plus ions. Minus 2 plus 4 is plus 2. We therefore need to bring that down to 0 to have the same charge as the right hand side, so we're going to need to add 2 E minus on the left, which works out because we were expecting the gain of electrons, so the electrons to be on the left hand side, because we're writing a half equation for reduction. So that is how I would go about doing that. Now I've kind of squidged those electrons in there, which is kind of irritating me a little bit. I could have just written the electrons at the front here, which probably would have been a better thing to do. But at the end of the day, presentation is not what is most important here. So long as it's legible, that is not going to put an examiner off giving me the mark credit. So if you're someone like myself who worries about presentation of answers, try not to. So long as it is legible and you've been really logical with how you've presented your information, you will be absolutely fine. Okay, so those are the bits I wanted to show you live. The next 2 I'm going to write my model answers in and come back to you, but one thing I do just want to say, I'm now going to be writing the redox equation for the oxidation and the reduction that we've just written the half equations for. Key thing is ensuring the electrons are equal so that they cancel. Thankfully we've got 2 electrons here and 2 electrons here, so the 2 electrons being lost are then being gained. If we had numbers of electrons that were not equal, we would need to multiply up one or both of the equations to get the electrons to be equal so that they cancel. There should be no electrons at the end in a redox reaction equation. Okay, I'll do those worked answers and I'll be back with you in a second. Okay, so I've combined the oxidation and reduction half equations together to give us this redox equation here. Now I did write the electrons in here to show you that they will cancel. Personally, if you have balanced the equations accordingly, I wouldn't normally write that in because you would have to cross through them and then rewrite the equation. Now I knew I was going to have to rewrite the equation anyway, because when I wrote everything that appears on the left hand side and then everything that appears on the right hand side, we can see that we had two separate molecules of chlorine which we would need to group together to become 2Cl2. But then looking at the balancing numbers, we had 2, 2, 4, 2 and 2. So we should always then simplify that where we can. So my final answer is Cl minus, ClO minus, 2H plus makes Cl2 and H2O. And that would be my final redox equation there. Now onto this application question. As I said earlier, the fact that it told us when we were using hydrochloric acid, which was a source of chloride ions, and we wrote a half equation for the oxidation of the chloride ions, when it then said that the solution of sodium chlorate was added to a colourless solution of potassium iodide, I was thinking, well, that's going to contain iodide ions. So can the iodide ions behave in the same way that the chloride ions did? And that's exactly what they're going to do here. So instead of seeing a pale green gas that bleaches universal indicator paper, we're going to see a colour change from colourless to dark brown, which is the colour of our iodine in solution. We need to say that it is the formation of iodine that does that, because we have to explain the reaction that leads to the observation. So I've said dark brown, bracket, change from colourless, bracket, due to formation of iodine as iodide ions will be oxidised. And of course there's nothing to stop you from writing an equation to show that 2 I minus ions would become I2 by losing 2 electrons in total. When I was going through this question before filming this video, I then wrote out the redox equation to show these being oxidized and to show that the chlorate ions would be reduced in the same way. That was a little more than was necessary for the 3 marks, but I just wanted to see how that equation would look when I joined them together, just to be certain that I hadn't missed anything. But again, use the number of marks, and this applies to all questions, use the number of marks to guide you on how much you're going to need to say. So suggesting what is observed and then explain the reaction that leads to this observation. We need to understand in all types of reactions, not just group 7, but group 2, also testing for group 7 ions, the year 13 reactions of metal ions and aqueous solution topic. We need to know what is responsible for the observations as well. So that's where 2 of the marks are going to come from. We're observing this because we've made this, and then the third part is to say, well, how have we made that? So we see it go dark brown because we've made iodine. How did we make iodine? We oxidized our iodide ions. Hopefully that's been helpful, but if anyone has any questions about anything in this video or anything to do with redox reactions more generally, please do let me know. Hope you have a really lovely day, guys. Thank you so much for watching.